Thanks everyone for coming on Zoom.
Okay, so good morning, everyone. Welcome to Amy Fang's B exam. So Amy's been here for 5 years, coming from MIT, got undergrad at MIT, and then immediately came here, right? Yeah, so we've spent some time at Lincoln Labs for some internships, went back to Lincoln Labs to actually make money and do work. And so without further ado, just that's kind of, I think you've all been to these things before, but about 45-minute presentation, questions from the audience, we kick you out, questions to you, we kick you out. We talk and we let you know what we decide.
Sounds good. Okay, well, thank you everyone for coming, both in person and online. So I'll be presenting the work that I've been doing the past 5 years in my PhD, which is looking at high-level collaborative task planning and synthesizing high-level behavior for robots in a multi-robot setting. I'm specifically looking at heterogeneous robots, meaning robots with different capabilities. So we can see that robot teams are useful in a variety of different applications. For example, I'm sure we're all familiar with the Amazon warehouse robots that move around the warehouse to deliver packages more efficiently. And this is sort of a homogeneous team of robots in a structured environment. So all the robots are the same and they're moving these shelves from one location to another. We also have heterogeneous teams. And so here on the right, we can see an example of a team from the DARPA Subterranean Challenge, in which the task was to rapidly search, navigate, and map an underground environment. And in this case, a heterogeneous team of robots may be particularly useful because the environment, there's more variety in the environment and we may need different capabilities to accomplish certain tasks. We can also think about heterogeneous teams in a disaster relief or emergency situation. When the robots are executing their existing tasks, there may be new emergencies that arise, and we want to look at how can we interleave these tasks rather than execute them sequentially to increase the efficiency of the robot behavior. There might also need to be collaboration across robots depending on the capabilities and the task that's required. And we also want to ensure that the overall team of the robots can recover from failure. So if a robot sensor breaks down, for example, during the middle of execution, how can we still ensure that the overall team will satisfy the task? So when I'm looking at these 3 aspects of the system, I want to address these 2 questions. How can we formulate or express these types of tasks? And how can we synthesize behavior for the robots that are correct by construction? So within these 3 aspects, I break it down further into 4 questions, and I'll go through this during my talk. So the first question is, how should a team of robots respond to a task if they're already performing existing tasks? So we can think of a very simple example where we have 3 heterogeneous robots in this 2D environment. They are currently executing existing tasks. And so their trajectories are shown on the left. And during the middle of execution, they receive a new task decomposed into subtasks. And so how can we sort of automatically update their behavior to execute both the new tasks that are introduced as well as accomplish their existing tasks? And we want to allocate these tasks in a way to minimize the overall cost of the team. Now, there's a wealth of literature in the multi-robot task allocation domain. The common approaches are some optimization methods where we model the system using some mathematical model, such as the vehicle routing problem or using constraint programming to find an optimal solution. There are also a number of meta-heuristic algorithms like genetic algorithms or particle swarm optimization methods to iteratively find a near optimal solution. There are also a number of distributed methods such as swarm algorithms or auction-based algorithms where one robot or a set of robots are designated as the auctioneer. The other robots will place bids, and then based on those bids, the auctioneer robot will choose the task or the robot to be assigned to that task. Now, recently, temporal logic has been of growing interest in encoding tasks, particularly for tasks that have temporally extended components. And one reason temporal logic is interesting is that it's a mathematically rigorous way to represent the task. And we can synthesize behavior of the robots that are correct by construction based on these sort of high-level symbolic abstraction of the system. So the common approaches are to use a graph search method, so representing the system as an automaton or an NDP and finding a path through the graph. There's also some hierarchical methods where we use the temporal constraints to generate a coarse high-level plan, and we generate the low-level executable paths by constructing a multi-robot reachability problem. in my work, I'm specifically focusing on linear temporal logic. So I'll give a brief background as to what that is and some common synthesis approaches for single robot tasks. So linear temporal logic is a discrete logic composed of both Boolean and temporal operators. The semantics are shown for the temporal operators here. The semantics are defined over infinite sequences. So we say that next is true if in the next state X is true. Always means that at every state in the sequence X is true. Eventually means that at some point in the sequence X becomes true. And X until Y means that X must remain true until Y becomes true. And so we can use these operators as building blocks to construct more and more complex specifications or tasks in LTL. So for example, we could have this specification that says, eventually we want the robot to go to room 1. And as a safety constraint, always avoid room 6. And make sure not to enter room 1 until you've entered room 5 first. So we can automatically translate this LTL formula into its Buki automaton equivalent. A Buki automaton is essentially a finite state machine, except that it accepts infinite inputs. And so we can evaluate whether or not an infinite sequence or a trace satisfies this formula by looking at the Buki automaton. So the labels on the states don't actually matter. What we care more about are the transitions. And we say that we can transition from one state to another state in the Buki automaton if that formula along the transition is satisfied. And so we say that an infinite sequence satisfies the formula if it reaches the set of accepting states infinitely many times. In this case, the accepting state, we only have one accepting state denoted by the double ring, which is state 0. And so essentially the Buki automaton allows us to evaluate whether or not which propositions or states have to be true in what ordering in order to satisfy the specification. And so since we can evaluate whether or not a trace satisfies the formula, we can also construct sequences or traces to satisfy the formula. That's kind of how formal synthesis works. Now, this represents what information is in the task, but we don't actually have any information about how the robot can physically execute the task. For example, if we had a robot in this grid environment, we know that the robot can't move from room 3 to room 1 directly. It also can't be in 2 rooms at the same time. None of this information is actually encoded in the task itself, so we need to include the robot in some information in some way. To do this, we typically represent the robot as a crypt key structure. And so you can see here that this environment is sort of abstracted into these states, and the transitions are also shown on the right. So we have the robot model that represents how the robot can physically move through the space, as well as the Buki automaton, which tells us what the task requires and what ordering of propositions need to be true or false in order to satisfy the task. Now, so we can combine this information by using the cross product to generate the product automaton. And if we can find a trace through the product automaton to the set of accepting states, then we can say that we found a trace for the robot or behavior for the robot to satisfy the task. So if we go back to this example, I'll illustrate a possible feasible trace for the robot to satisfy the task. So let's say that the robot starts in room 3. It then moves to room 2, which means that it's satisfying the self transition that's highlighted. It now moves to room 5, so it can execute the transition between 1 and 2 in the Buki automaton. It moves to room 4, and finally it moves into room 1. And now we've reached the accepting state. So as long as the remainder portion of the robot behavior stays in this accepting state, we can say that the behavior satisfies the task. And so here you can see that the accepting transition or the self transition is just saying always avoid room 6, which was our original safety constraint. So this is sort of a brief background on what LTL is, how we do automata-based synthesis for a single robot. Now, if we go back to this question in the multi-robot domain, which is how can we interleave tasks and assign these robots to the new tasks that are introduced? I'm assuming that the tasks are decomposed into subtasks that are independent, meaning that the robots don't have to coordinate with one another, and they're non-conflicting, meaning that the satisfaction of one subtask must not violate the satisfaction of another subtask. So the goal is to assign these new subtasks to the robots while minimizing the overall cost of the team, synthesizing their corresponding behavior, and doing all of this in a distributed manner. There is some existing work that considers similar problems where the tasks are decomposed first and then assigned. Typically, these approaches, when you're looking at optimization, tend to be centralized. The decentralized approaches are often for homogeneous teams that are trying to satisfy a global specification. So I wanted to consider sort of all of these factors that are shown on the slide, as well as this question of responding to a new task if they're already performing their existing tasks. In this way, we don't have to have the robots execute the tasks sequentially, which may be less efficient than if they were to interleave the tasks together. So here's an overview of the synthesis process for each robot. So each robot will construct a new Buki automaton based on the progress within their current task, as well as the new kth subtask. Then we can use that Buki automaton and the robot model to generate the overall product automaton to find a valid trace or the behavior for the robot. So for example, we could have this Buki automaton for robot 2. It receives the new task when it's in state 1 of the Buki automaton. So we can just take the reachable portion of the Buki automaton to the accepting state. This sort of represents the remaining portion of the current task that hasn't been executed yet. Then we combine that with the Buki automaton of the kth new subtask. And then we can generate the product automaton by taking the updated Buki automaton and taking the cross product of that with the robot model. Now, in this case, we're assuming heterogeneous robots that are based and heterogeneous in the sense that they may have different capabilities. So the robot model sort of includes all this information based on the capabilities. The capabilities are weighted transition systems, and we take the product of all of these to generate the overall robot model. And you'll notice that there are also costs associated with each transition. So not only can we find a valid accepting trace for the robot to execute a certain behavior, we can find a minimum cost trace. And in this way, we can sort of look at how to minimize the cost for the overall team.
Amy, can I ask a question?
Yeah.
Can you go back to the previous slide?
Mhm.
How is the middle, your added task added?
Yes. So we sort of take this intersection.
So is it an image? It's not an image.
No, it's not in the image. No. But we have a Buki automaton that represents the new subtask. The new subtask is also encoded in LTL. So we first automatically transform that into the Buki automaton and then use this intersection operator to combine the two.
Is it unique
What do you mean by
in terms of integrating the two? Or are there multiple ways of integrating?
I think it's unique.
I just don't know too much about automata, but I could imagine you could have potentially multiple connections.
So there may be multiple paths or multiple traces.
Maybe explain how you do the intersection.
Yes, I should have included this in the backup slides, but essentially the intersection is kind of similar to how we do a cross product, where now each state will have, where each transition, when we combine the two Buki automata, we check to see if any of those transitions violate each other. And if those transitions violate each other, then we can't combine those two transitions together. So we're basically sort of conjuncting these transitions together, but if they violate with each other, then that transition is not valid.
So is it unique?
Yes.
Okay, thanks.
Okay, so
It's not putting a state inside of another state. It's just taking both of them together and just removing everything that's impossible. So it has everything possible in it. Every possible kind of.
You end up with a bigger
Yes.
Buki automaton, then that's it.
yes.
And does that persist after task is finished?
Sorry, could you repeat the question?
Persistent.
So if you ordered the same task over and over again, it's gonna get later.
Yeah, I think that.
I didn't.
We're tabling a question.
Okay.
It's a bigger picture question that everything lasts later.
Okay, sounds good. Okay, so now the goal, once the robot synthesizes behavior for each subtask, we now want to sort of assign these tasks in an optimal way where we want to minimize the cost of the overall team. And to do this, we have a decentralized token-based task allocation assignment algorithm where we pass around a global assignment token alpha to each robot. This token sort of represents which robot will perform which task. And the robots will assign themselves a subtask that it can perform. And if a robot's already assigned a subtask, it makes these pairwise comparisons of these assignments, and the robot that has the lowest cost is chosen. Now, This doesn't necessarily provide the globally optimal solution because the solution may change depending on the ordering in which the robots receive the token, but we have some near optimal results. And to just illustrate sort of what the updated behavior of the robots may look like, we can look at robot 1, and the original task is shown on the left, and the new task is shown on the right. And you'll notice that the robot will now interleave the two tasks. So it first scans in room 1, then it goes to pick up the package in room 2, and now it's going to room 1 to scan again, which finishes its current task, and finally it drops off the package in room 3. So now it's accomplished both of these tasks, not necessarily sequentially. So just as a summary, in this work, we proposed a framework for robots to update their behavior and to assign themselves to tasks in order to try to minimize the overall cost for the team. Here we're assuming that the task is decomposed into independent subtasks, so the robots aren't collaborating with one another. But what if we did want to include some type of collaboration between the robots? Now, there's been some work in this area, specifically with temporal logic. Typically, the approach is to extend an existing type of temporal logic. So on the left, you can see an example of an extension of signal temporal logic. On the right, we see an extension of linear temporal logic. And you'll notice here that in both cases, we have to encode some information about either the number of sensors or the number of robots, as well as the type of sensors or robots that we need. But there could be cases in which the user may not actually care about this type of information. It cares more about the actions that need to happen. So to motivate this, we could think about a warehouse environment where we have maybe this older version of this mobile manipulator of a Boston Dynamics robot that is moving a package from one location to another. And let's say that the user first wants to move a pallet to the ground before delivering this package. And we also have a forklift robot in this environment. Now, the user might care about requiring that the same robot needs to perform both of these actions. So either the forklift robot needs to pick up needs to move the pallet and then deliver the package, or the mobile robot needs to do those. But the user might not actually care about who does what. It just cares that these actions happen, and how it happens doesn't really matter, in which case maybe the robots could autonomously coordinate with each other, where first the forklift robot moves the pallet to the ground, and then the mobile manipulator delivers the package. And so I wanted to look at this type of task where we can sort of remove that level of user information about the number or types of robots that are required. So given these types of tasks, we first have to figure out how can we express this type of task or encode it in temporal logic, and then provide a synthesis framework to synthesize behavior for the robots. So for this, I proposed a new task grammar called LTL-SCI, which is an extension of linear temporal logic. So you'll see here that an LTL-SCI formula has a base LTL formula, and it has this binding formula attached to it. And these binding formulas are composed of Boolean operators, and each binding provides a way to encode information about the relationship between the robot assignments and the overall behavior of the robot. So for example, we can see an LTL-SCI formula shown here. This says that all the robots assigned binding 1 must pick up a package in room A, and those same robots must drop off the package at the same time that the robots assigned bindings 2 or 3 take a picture. And so here, the bindings are shown as the numbers 1, 2, 3. The values of the bindings don't actually matter. What we care more about is where the bindings are placed along this formula. So for example, we see that binding 1 appears on 2 parts of the formula. So this indicates that whichever robots are assigned to pick up the package must also drop it off. And so in this way, we can sort of treat these bindings as a task allocation problem, but these tasks are sort of tightly interleaved, and we can sort of express a richer set of tasks rather than having to decompose the tasks into subtasks. And so the goal would be to find a team of robots and binding assignments to satisfy these tasks and satisfy the sort of binding constraints on the task. So you could ask, is it possible to only use standard LTL to encode these types of tasks? So if we go back to this original example, if we wanted to express this, this formula in standard LTL, it would look something like this. We would need a proposition associated, the propositions would need to be associated with every individual robot, meaning that as the number of robots increase, the number of propositions increase as well. The overall complexity of the task itself increases, also because we need to sort of specify that these are all the possible sub-teams or teams of robots that could be assigned the task. And this also doesn't generalize to any number of robots because we need to have these propositions associated with specific robots. And so sort of being able to express these tasks in LTL-SI makes it much more efficient to synthesize an overall team. So I've talked a little bit about the syntax of LTL-SI. Now we can move on to the semantics. The semantics are defined over two things. We have a team trace composed of the traces or the behavior of each individual robot and their corresponding set of binding assignments. And so here is the full definition of the semantics. We have Boolean operators and temporal operators shown here. The semantics are defined recursively, so I'll just go through this base case. In order to define the semantics, we also need this function zeta, which outputs the set of all possible combinations of bindings that can satisfy the binding formula psi. So for example, if the binding formula was 2 or 3, then we would need the robots assigning bindings 2 or 3 or both to satisfy the formula. And so we say that a team trace and the robot's binding assignments will satisfy a task encoded in LTL-SI if there is a possible binding assignment that satisfies the binding formula psi, such that all the bindings are assigned to at least one robot. And for any robot assigned one of these bindings, its trace satisfies the base formula phi. So in this case, we're assuming that multiple bindings can be assigned to a single robot and multiple robots can be assigned a single binding. Is that correct? Yes. One robot can be assigned multiple bindings and one binding can be assigned to multiple robots. Okay, so I've talked a little bit about the expressivity of how we can express these types of tasks using LTL-SI. Now I'll go on to the synthesis framework. How can we construct a team and a binding assignment to satisfy the task? The robots are modeled the same way as before. It's a product of their capabilities. And when we go through the synthesis process, we first construct the Buki automaton, and then we find a team of robots and binding assignments to satisfy the overall task. Once that happens, we can now, in a distributed manner, for each robot, it synthesizes its own behavior and executes synchronization policies when necessary. So when we construct the Buki automaton, each robot also determines the possible bindings it can do based on that Buki automaton. So for example, let's say we have this simple task that says that eventually we want all the robots assigned binding 1 to go to room A, or all the robots assigned binding 2 to go to room A. And here is its Buki automaton equivalent. Now each robot, for every transition in the Buki automaton, needs to determine the possible bindings it can do. So for example, if we have this robot currently in room C, if we're looking at this self transition that's highlighted here, it's not in room A, which means that the robot can satisfy both bindings 1 and 2. And we also keep track of every sub-combination of bindings that the robot can satisfy, because there may be situations in which the robot can satisfy binding 1 or binding 2, but not both. Similarly, if we look at this transition, the robot's still not in room A, so the robot can't satisfy binding 2, but it can't satisfy binding 1 because none of the propositions associated with binding 1 appear on the transition. So we store that information as well. So once all of the robots have determined their possible bindings based on the Buki automaton, we can now find a collective team of robots to satisfy a task. To do this, we have a depth-first search algorithm that finds a trace through the Buki automaton to the set of accepting states. So to illustrate this, I have a much larger Buki automaton for a more complex task. The accepting state is shown in the double ring, so the state 0. And we initialize the set of, or the team of robots to be the set of all available robots. So we have 4 robots shown here. And all of their binding assignments are just initialized to be all of the possible bindings, in this case, 1, 2, and 3. And we try to find a path to the accepting state or the set of accepting states. And as we traverse through the graph, the robots will remove the binding assignments that it can't do. And we say that an edge is valid if all of the bindings are assigned to at least one robot. So, for example, you can see in this video that we're sort of traversing through the Buki automaton, we come across a transition that is not valid here because none of the robots are assigned binding to. So this is not a valid team. So we have to backtrack and try to find a different edge to traverse until we reach the accepting state. So we've sort of found this collective trace for all of the robots to be able to accomplish, as well as their corresponding binding assignments. And when we're assigning the robots to specific bindings, we have this binding allocation algorithm where we sort of choose a robot to be assigned based on this sort of priority that's shown here. We want to make sure that we first choose a robot if it's assigned at least one unique binding. Here, when I say unique, it means that there's a binding that can only be assigned to that one robot and none of the other robots. So we want to make sure that that robot is assigned that specific binding. And once that happens, if there are no other robots that satisfy this first criteria, we move on to the second, which simply says we want a robot that can be assigned an unassigned binding, a binding that has not yet been assigned. Otherwise, if all the bindings have been assigned, we can choose a robot at random. And every step in this process, we always choose the maximum length set of bindings so that we try to ensure that all of the bindings can be assigned. So if we look at, again, the output of the DFS algorithm, we can see that there's some overlap in the binding assignments. So for example, multiple robots are assigned binding 1 and multiple robots are assigned binding 3. This can have this is actually beneficial for robustness. For example, if during execution something fails, one of the robots can no longer be assigned binding 1, we know that we have another robot that can still execute that binding. Similarly, or in addition, we also have this feature where based on some user metric that the user might care about, we can take a subset of these robots and ensure that those robots can still execute the task as long as all the bindings are still assigned. So for example, if the user says, I want to minimize the number of robots, we can choose the orange and the pink robot to execute the task. And we know that since all the bindings are still assigned across those robots, the task will still be able to be satisfied. Okay, so we found a collective trace in the Buki automaton for all the robots to be able to satisfy, as well as their corresponding binding assignments. Now, each robot can synthesize their own behavior and communicate with each other during execution when they need to synchronize with each other. Now, for example, the robots will need to synchronize on the transition from states 1 to 2 in the Buki automaton. And to do this, we look at the behavior for each robot between these two states. And now the goal is for the robots to synchronize on this green state. So what the robots do is they wait in their penultimate state, in this pink state, until all the other robots are also ready, and then they execute the green state together. Now, one thing to note is that specifically, for example, let's say this transition, we only need the robots assigned bindings 1 or 2 to be involved in the synchronization policy. If there's a robot that's only assigned binding 3, none of its propositions appear on this transition. So it doesn't need to be involved in the synchronization process. It can simply continue executing its behavior until maybe somewhere down the line, there's another transition that requires binding 3. So just to summarize, I proposed a new task grammar called LTL-SCI to encode these types of collaborative tasks. And we have a synthesis framework where we can sort of assign robots to specific bindings and synthesize their own behavior to satisfy the overall task. One thing to note is that this framework is largely agnostic to the number of robots because the only portion that is centralized is the DFS algorithm. And so the DFS algorithm itself is linear with the number of robots, but the other two components where the robots determine the possible bindings and sort of synthesize their behavior, all of that is distributed among the robots. The framework is exponential with the number of bindings because we have to keep track of every possible combination of bindings that the robot can execute. Okay, so I've talked a little bit about how we're encoding these collaborative tasks. In this framework, we're assuming that all the actions are instantaneous. But in physical systems, that's not necessarily the case. Actions have different timings and take different times to execute. So is there a way to extend my previous framework into the sort of continuous time action domain? Now, typically when we look at continuous time, a lot of people use signal temporal logic or other types of metric logic to sort of be able to define sort of tasks over discrete time continuous signals in which we can express information about certain timing bounds that we might care about. In our work, we choose to still use the discrete LTL abstraction because in this way we can still abstract the actions without having to maintain any information about the timings on the actions. So all we need to know is that the actions are either instantaneous or non-instantaneous, and we can still generate high-level controllers for the robots. There are some approaches looking at this problem in LTL. Typically, they're either for single robot tasks or for multi-robot systems where the tasks are assigned a priori and are independent. There's also some iterative approaches where you have to synthesize and then check to make sure that the behavior satisfies the task, which can be inefficient. So if we look at our previous framework using instantaneous actions, you could ask, could we just use that directly to synthesize behavior for actions that take continuous time? And so here I'll just illustrate an example in which there may be violations that occur. So this task here is saying that all the robots assigned binding 1 need to go to the dock. And if any of those robots are in the dock, as a safety constraint, the robots assigned bindings 2 and 3 must be taking pictures in room B. And so let's say we have 2 robots here, the blue and the green robot, and the corresponding binding assignments and behavior is shown here. So this is sort of the output in sort of assuming instantaneous actions, where we could have the blue robot outside of room 1 or in room A, the green robot in room C, then immediately transition into the respective rooms. And because it's instantaneous, this behavior does satisfy the formula. But if we assume that the behavior takes, moving between these 2 rooms may take different amounts of time, we could see that the green robot would enter the dock before the blue robot enters room B, which would violate the safety constraint. If we could somehow enforce the behavior where the blue robot first moves into room B and then the green robot moves into the dock, this behavior would not violate the safety like it does now. So now the goal is, can we automatically enforce some sort of ordering to these non-instantaneous actions to both to ensure that the task is satisfied with continuous actions. When we abstract these actions that execute with different timings, we have these 2 types of propositions. We have a proposition that's associated with the action currently being executed, as well as its corresponding completion proposition, which just says that the action is completed. And so given some timing function, we can say that we can define instantaneous actions if it doesn't take any time to complete, and then if it's not instantaneous, then it takes some non-zero amount of time to complete the action. So for example, taking a picture could be classified as an instantaneous action. Moving between 2 rooms is a non-instantaneous action. And with instantaneous actions, the propositions pi and pi c have equivalent meanings. So from our original synthesis framework that I showed earlier, we have to sort of add this block shown in red, in which we have to update the Buki automaton as we try to find a valid trace through the Buki automaton using that DFS algorithm I mentioned earlier. And so to do this, we sort of have 2 steps. We first check to see,
So you don't have to do it. The way you're choosing to solve this is by updating the Buki.
Yeah.
So
Yes, we don't have to do any of this. But one approach would be to sort of enforce a specific ordering when we're trying to find a trace through the Buki automaton to ensure, for example, in the previous example, we had that the blue robot moves to room B first. When we check to see if we need to sort of enforce an ordering, we look at the Buki automaton and we look at consecutive transitions in the Buki automaton to check to see if we need to enforce a specific ordering. And there's 2 types of transitions. There's self transitions to non-self transitions, or the other way around. And the approach is slightly different for these 2 cases, so I'll illustrate them both. So let's say, for example, we start with the self transition to the non-self transitions, and the transitions are highlighted in blue. In order to check to see if we need to enforce an ordering, we ask 2 questions. First, are there multiple non-instantaneous propositions that appear on the second transition? And do any of the non-instantaneous propositions explicitly change truth values? Meaning, do they appear on both of the transitions and require a different truth value for that proposition? So in this case, we can see that we're requiring doc C1 to be false on the first transition and then true on the second transition. So in this case, we can take advantage of the fact that the first transition is a self-transition to generate intermediate transitions that enforces that the yellow propositions become true first before the red transitions become true. And here we're still enforcing that the self-transition label remains true. So you can see here that on the pink transitions, we're still enforcing that not doc C1 is true before they can execute the original transition together. So this was the case for the self-transition to the non-self transition. Now we can look at the other way around, where we have a non-self transition to a self transition. We can ask the same two questions. For this specific example, we don't satisfy the first question because there aren't multiple non-instantaneous propositions. So we don't actually need to update the Yuki automaton. But for the sake of illustration, let's say we had a second non-instantaneous action shown here. And we update the Yuki automaton like this. We can't have intermediate transitions like we did before because we don't have a self transition on the first transition. So we need to add the proposition directly onto the first transition. Now, this doesn't actually violate the original Yuki automaton in any way. We're just adding more constraints onto this transition, and it doesn't violate the original formula because this proposition didn't appear on it originally. Okay, so that was sort of the first step, which was checking to see if we need to enforce an ordering of non-instantaneous actions in order to ensure that the actions, when they are executed in continuous time, don't violate the original specification. We also might need to enforce some binding assignment constraints. So, for example, if we go back to this Yuki automaton, we can see that here we're requiring that all the robots assigned binding 1 need to be in the dock. And then immediately afterwards, they need to not be in the dock. And so if we had multiple robots assigned binding 1, it's sort of unrealistic in a physical execution that all the robots would be able to simultaneously be in one room and then simultaneously not in that room. So in this case, we enforce the constraint that one and only one robot can be assigned binding 1. This doesn't affect how we come up with the team and the DFS algorithm. So we just output this information to the user at the end, and the user can choose if there are multiple robots assigned binding 1, the user chooses which robot will execute that binding. So here's the same example I showed before, implemented on a physical system. You'll notice here that the orange robot won't be doing anything. It was originally assigned binding 1, but because, like I mentioned earlier, we have to enforce that only one robot is assigned the binding 1, that we've chosen to use the blue robot to do that instead. And here we have 4 robots. 3 of them are Hello Robot stretch robots. And one of them is a clear path boxer robot attached with a Canova Gen 3 arm attached to it. And we use an OptiTrack motion capture system to keep track of the robots. And so you'll see here that the blue robot will sort of wait outside the dock in room B until all the other robots are in room B ready to take pictures. And so these black boxes represent the cameras of the green and the pink robots. And so you can see that as soon as the blue robot enters the dock, the other 2 robots are taking pictures. We're assuming here that because we're only constructing behavior on the high level abstraction of the actions, we're assuming that we have low level controllers to execute these actions. So for example, we don't have any information about collision avoidance in the high level behavior of the robots. So we assume that that's already implemented in the low level controllers. So here's a little bit more of a complicated example, which says that eventually we want all the robots assigned bindings 1 or 2 to beep at the dock at the same time, and then we want the robots assigned binding 1 to pick up a package in the storage room. And in addition, we have the safety constraint that says that none of the robots can enter room B until the robots assigned binding 3 have finished pushing the cart in the hallway. So we'll see that the pink robot, which needs to go to the dock, would have to go through room B. So it waits to execute that action until the green and the orange robot push this cart. And so again, it's because we're assuming we're doing high-level abstraction of the system, we're assuming that the low-level controllers are coordinating, are executing sort of the coordination of pushing the cart together. So now that the cart is pushed out of the way, the pink robot now goes to the dock and beep. And now the remaining two robots can sort of begin picking up these packages at the same time. Okay, so I've talked a little bit about how we can extend our previous framework, which only considers instantaneous actions, to assuming that the actions may have varying duration, and how we can still automatically synthesize behavior that is correct by construction for these robots. Now, in all of the previous work that I've shown, we're assuming that the robots cannot change their behavior at runtime. And so it would be useful if they could replan, specifically based on sort of modifications that might happen during execution, where a robot sensor might fail or something like that. It could be useful for the robots to resynthesize or replan online to sort of still be able to satisfy the task. In existing work, we have a lot of different definitions of what failure means. So some common definitions are that the entire robot fails, so it can't perform any part of the task. There's also this notion of the entire capability fails. The capability is represented as sort of this binary value, so it either can use it or cannot. I wanted to look at sort of one level further, which is what happens if transitions within the capability fail, but the capability overall could still be used in some other way. For example, if we had a static manipulator, and let's say its gripper fails, but it can't pick things up anymore, but it could still push things. And so this capability can still be represented in the robot model, but just not able to use that pickup action. We're also considering not only failure, but augmentation, in which transitions can be added back into the capability. For example, maybe during execution, the user decides to put on a new gripper, in which case the robot is now able to do the pickup action again. And so how can we sort of address these types of modifications and sort of replan around these types of failures and augmentation? So more formally, let's say we have this motion capability, and we say that the set of transitions that failed are represented as this delta fail. So if we have this environment where the robot can move between rooms A and B, let's say that a door closes, for example, the robot's no longer able to move between those two rooms, and so the transitions highlighted in red are removed. Similarly, for augmentation, we could say that, let's say a door opens, the robot can now move between rooms A and C. So these transitions and states in the capability are now added into the capability itself. So the overall replanning framework is as follows. We want to sort of minimize the amount of replanning that's required and sort of resynthesis that happens for each robot. And so we try to see if we can only modify just the local behavior of the modified robot. And if not, we check to see if we can update the global behavior or the other robot's behavior if necessary. So to go through this framework, I'll sort of have this example shown on the right. We have a specification that says that all the robots assigned bindings 3 must go to the storage room and beep. And all the robots assigned binding 1 must eventually go to the dock. And anytime all of the robots assigned binding 1 are in the dock, we want the robots assigned binding 2 to take a picture in room B. And so, for example, if we had a modification where we augment a capability, for example, now the blue robot can move between rooms B and G. This doesn't actually affect the ability of the robot to execute its original behavior. So it doesn't change its behavior, it just stores its information and continues to execute. If there's a failure, for example, if we had the orange robot is no longer able to move between room D and the hallway, we first check to see if the failure affects the robot's behavior. In this case, the orange robot was originally going to move between these two rooms to reach the dock. So it does affect the behavior. And we update the robot's behavior to sort of work around that. Then we check to see if the failure affects the team's behavior. So in this case, this orange robot is still able to execute binding 1, which was to eventually go to the dock. Because instead of going from room D to the hallway, we now go from room D to C to get to the dock. And so it's still able to execute binding 1, in which case this failure does not affect the team's behavior, only the affected robot's behavior. But there could be situations in which it does affect the team's behavior. For example, if the pink robot's camera fails, it's no longer able to execute binding 2, and only that robot was assigned binding 2. We need to sort of reallocate the assignments so that binding 2 is still able to be assigned to a robot. So in this case, we do a reassignment where now the green robot will execute binding 2 of taking the picture in room B, and the pink robot is assigned bindings 1 and 3. And so something else I want to point out is that when we're doing sort of the highlighted portions of the framework, we need to sort of update the robot's model based on the modifications that happen. And so to do this, we need to update both the robot model itself and the possible binding assignments it can do, which is important for the reallocation process. So rather than update the robot model itself, we can update the product automaton, which means that we don't have to reconstruct the entire robot model and therefore reconstruct the entire product automaton. So to do this, we just extract the portions of the product automaton that have been modified. So we take the portions of the robot model that has either failed or been augmented, take the cross product of that with the remaining reachable portion of the Buki automaton, which represents the remaining portion of the task that still needs to be executed. And so we can just take those portions of the product automaton and remove or add them as necessary. And finally, I just want to sort of show the robots executing the task with these modifications. So every time it flashes, that means a modification has occurred. So in this case, the blue robot can now move between those 2 rooms, but its behavior doesn't change. In this case, the orange robot was originally going to move into the hallway, but now it's moving through room C instead. And finally, the pink robot's camera fails, so now you'll see that the green robot stays in room B while the other robots go to the dock. Okay, so in this framework, I've basically addressed this question of how we can replan online for these robots to respond to modifications within their capabilities during execution. And so looking at all of these questions, this sort of zooming back out to the original aspects of both the tasks and the overall multi-robot system, we've been able to sort of address these 2 main questions about how to express these types of tasks and synthesize behavior for these heterogeneous robots. There's a lot of avenues in terms of future work. One of them is about scalability. So I mentioned before that in a lot of this framework, it scales well with the number of robots, but it doesn't necessarily scale well with the complexity within the robot. So we sort of have the state space explosion problem as the task itself becomes more complex and therefore the Buki automaton grows, or the capabilities or the number of capabilities become more complex, which means that the robot model itself also grows. And so we could look at applying some sampling or heuristic-based techniques to sort of synthesize behavior as complexity scales. Another interesting avenue to look at is how our assumptions may affect the guarantees. We make a lot of key assumptions about the system. Namely, we have perfect communication, perfect actuation, the environment is structured and fully known. So that might not be the case in a lot of real world scenarios where we maybe only have partial observability or sort of sensor noise. So how can we sort of combine maybe belief-based planning with formal synthesis guarantees, and how can we see exactly how these assumptions affect the guarantees and which guarantees may no longer hold because of that? So that sort of concludes my talk. I sort of conclude with the publications that I've had over the past 5 years, and as well as, of course, thank my committee and the rest of my lab for their support, as well as my funding source, NDSEG. And just for fun, here's a picture of some of my committee members at commencement. Kirsten unfortunately isn't in this photo, but here's me photobombing Mark and Dos and our DGS Nelly. But with that, thank you.
Did you put it on us?
That was impressive, I have to say. Perfect time.
Yeah, and with that, I'll take any questions.
All right, questions from the audience?
So I wanted to know more about the LTL specification language that you
Okay.
came up with. I want to know more about, so basically, does it have capabilities that the original linear temporal logic does not have? Because you mentioned that it's. Yeah.
Sorry, there's a lot of slides. Is this the slide you were talking about?
Yes, so basically, it's clearly visible that you reduced your specifications to a much more compact representation. But I wanted to know if there are things that your specification language can do that the linear temporal logic can't do, or is it just a more compact representation?
Yeah, that's a good question. So, so in this case, if we wanted to encode the specification in LTL, we would have to generate every possible combination of robot assignments. So theoretically, that's still possible in LTL, but the key difference is that it doesn't generalize. So anytime you have introduced more robots into the system, you'd have to rewrite the task in LTL, regenerate the Buki automaton and such. And so in this case, we also, in using LTL side, we don't have to include that information, and so the Buki automaton stays the same regardless of the number of robots.
I think the question was the opposite. Are there
Oh.
things with LTL side that you can't do with LTL?
That's what you answered.
Well, you said, okay, so LTL is, harder to write everything out if LTL, like compared to LTL side, but are there limitations to LTL side?
There are limitations that,
Are there things, are there things in LTL, that you can write in LTL, not write in LTL size?
Isn't that what you said?
No, yeah.
No, I asked the
Okay,
other,
okay.
but
Oh, I was curious about.
yeah,
yeah.
that's a good follow-up. Then is there something?
So I would say not necessarily for standard LTL, but if we look at sort of the other types of the other work that's been done in sort of in encoding other types of collaborative tasks, LTL side and their work can express different types of tasks. So here, since we're encoding information about the number of robots and robot type, that's not something that we can do in LTL side. So we can't actually enforce any information about the number of robots we want for each binding, for example. So it's just a different way to express different types of tasks depending on what the user wants.
Okay, so.